Hi, we're learning about life science and cell biology in a nutshell, and we were currently studying the bilayer of cells, so which are comprised of phospholipid molecules, and we're learning about their fluidity. So fluidity of the bilayer um, is controlled by their composition. So, um, the phospholipid molecule composition, as well as the environment factors such as temperature. So, the phospholipid bilayer, which can be studied, they make synthetic bilayers and they change from a liquid state to a more rigid crystalline or gel state, depending on the fluidity of that particular membrane. So each composition uh, has a different characteristic freezing point, so aka a different fluidity. When the state is changed, this is called a phase transition from liquid to gel or crystalline, more solid. So if the hydrocarbon chains, aka the fatty acid tails of the phospholipid molecule, are shorter and have double bonds, the freezing point is lower, which means it's more difficult to freeze. So this means that the phospholipid molecule is less likely to be rigid and is more fluid. The tails are shown here. So these are the fatty acid tails, which are two chains coming off a glycerol backbone bound to a phosphate group bound to an alcohol. The polar head is one side of the phospholipid molecule. The nonpolar tail is on the other side. So the fatty acid chains that are on the phospholipid molecule determine how fluid the layer is going to be and the behavior of the membrane. So again, the polarity, any kind of double bonds in the chain of the hydrocarbon chain of the fatty acid tail adds more polarities and more fluidity to the membrane, because the kink from the double bond prevents the intense stacking of the molecules, so it becomes more fluid. So there's less rigidity and less linearity of the chains. They don't stack as tightly due to the kink of the molecule caused by the double bond between two carbon groups. So, however, if you have straight chains, which are so the double bond, it's called an unsaturated fatty acid, while with this all single bonds in the chain is called saturated. So these cause more rigidity in the membrane, the saturated fatty acid chains. So a shorter chain length of the hydrocarbon chains makes them more difficult to pack together as well. The membrane remains more fluid at lower temperatures. So bacteria, yeast, other organisms whose temperature fluctuates with that of their environment adjust the fatty acid composition of their membrane lipids to maintain relatively constant fluidity. As the temperature falls, for instance, fatty acids with more cis double bonds are synthesized, so the decrease in bilayer fluidity that would otherwise result from the drop in temperature is avoided. So, more double bonds in the fatty acid chains, as well as their shortness and length, adds more fluidity to the bilayer. Here shown, you have saturated versus unsaturated hydrocarbon chains. Um, so the unsaturated have cis double bonds. So you have more fluidity and less rigid packing with unsaturated bonds. With saturated, more linear chains cause more rigid layer and tight packing, and which is not helpful if it's a very low temperature environment and the membranes are more prone to freezing. The influence of cis double bonds in hydrocarbon chains is shown. The double bonds make it more difficult to pack the chains together, making the bilayer more difficult to freeze. The fatty acid chains of unsaturated lipids are more spread apart, therefore the lipid bilayers containing them are thin. Are less solid, so thinner than bilayers formed exclusively from saturated lipids, which tend to be more solid and bulky. The lipid bilayer of many cell membranes is not composed exclusively of phospholipids. However, it often also contains cholesterol and glycolipids, which are lipids bound to uh, sugars. So glyco means the carbohydrates are bound to lipids. Eukaryotic plasma membranes contain especially large amounts of cholesterol, up to 1 molecule for every phospholipid molecule. The structure of cholesterol is shown in this diagram. Cholesterol contains a polar head group in red, a rigid steroid ring structure, which is a 4 rings, carbon rings. 3 have 6 carbons, while the 4th ring has 5 carbons, as well as a nonpolar hydrocarbon tail. Cholesterol is a stirred molecule, which we learned about earlier. This is the drawing. Cholesterol is shown with the formula as well as the schematic and space-filling model. The cholesterol molecule enhances the permeability and the barrier properties of the lipid bilayer. They orient themselves in the bilayer with their hydroxyl groups close to the polar head groups of the phospholipid molecules. So the polar heads are going to be close together, attracting. In this position, their rigid plate-like steroid rings interact with and partly immobilize those regions of the hydrocarbon chains closest to the polar head groups. So one molecule is phospholipid, one molecule a phospholipid, and in the middle you have the cholesterol molecule. So the polar head groups line up. The cholesterol is in the middle, causing a stiffened region, and the more fluid region of where the fatty acid tails are interacting. So the schematic shows how cholesterol interacts with phospholipid bilayers in one monolayer of a lipid bilayer. As a note about phospholipid molecules, phosphatidylserine, which is one type, carries a net negative charge. The other 3 types of phospholipids are electrically neutral at physiological pH, carrying 1 positive and 1 negative charge, which neutralize each other. And together, these 4 phospholipids make up the bilayer of most membranes. Inositol phospholipids are present in smaller quantities but are functionally important, which have a crucial role in cell signaling. Head group polarity also determines membrane polarity and